Okay, so the time is 6:10. We can now begin test 2. First question. In practicals, you send a cart of mass 0.55 kilograms along a track with an initial velocity of 72 centimeters per second. It rolls for a while. I guess it's slowing down. Then collides with a fixed force sensor at the end of the track and reverses its direction. I remember that. Shown as the motion sensor data, giving velocity versus time. The sensor was set to record 60 samples per second. Which of the following is the best estimate for the change in momentum? So find delta P in the cart during the brief collision at t equals 1.3 seconds. So it's talking about this particular collision and trying to find delta P. And remember, P is a vector. So it starts off positive, goes to negative. Okay, so let's try to estimate here. That's, I guess, V initial is going to be plus 60 centimeters per second, which is equal to plus 0.60 meters per second. And then at the end, just after the collision, it seems like V final is equal to maybe negative 55 centimeters per second. So negative 0.55 meters per second. So just to sketch this out a little, initial, you've got a cart which is 0.55 kilograms and it's going to the right, and V initial is equal to 0.6 meters per second. So the P initial there is going to be plus 0.55 times 0.6. So 0.55 times 0.6. It's going to be plus 0.33 kilograms meters per second. And then that's your initial situation. Your final situation is just the cart is now reversed its direction because it bumped off the bumper or something like that. It's still 0.55 kilograms, but V final is now this negative 0.55 meters per second. So P final is a negative number, 0.55 times, actually 0.55 would be numerically the same, so it's 0.55 times 0.55, and you get P final is negative 0.3025 kilograms meters per second. So what that means is delta P is P final minus P initial, which is negative 0.3025 minus 0.33. So I get negative 0.6325 kilograms meters per second is the change in momentum that we're trying to find. Let's see if that matches up any of these. Yeah, so the closest answer, version A here, is D. Okay. Question 2. A car is rolling over the top of a hill at a constant speed V. At this instant, how do the magnitudes of the normal force upward and the gravity force downward in the car compare? Greater than, less than, equal to? Usually it's equal to, right? Oh, but this is going on a circular path. So circular path. Which, what that means, anytime you're going at a speed v on a circular path, that means that you define plus r to be down, and you've got the acceleration in the r direction, it's down. So so what you need is the net force in the r direction to be equal to m times ar, whatever, v squared over r. And again, since plus r is down, that's going to be your positive Fg minus your normal force is equal to mv squared over r. So you can, I guess, solve that out for normal force. You can add normal to this side, subtract, you got Fg minus mv squared over r. So normal force is equal to Fg minus this positive thing, mv squared over r. So it's definitely less than Fg. So B. Okay, you need a greater force downwards so that the net force takes you towards the center of the circular motion. Okay, next question here. Question 3. A ball hangs from a string of length 1.2 meters and swings in a horizontal circle. As the ball travels, the string makes a constant angle of theta equals 32 degrees away from vertically down. What is the ball's speed? Okay, so it's moving in a circular path. So this is your r direction there. What's funny here is actually r is not given, but I think we can find it. So let's find r from geometry. I would say that would be a first step. So if we know this triangle, this is L, this is theta, this is the right angle, and this is r, the radius of that horizontal circle, then sine of theta is opposite over hypotenuse. So r is equal to L sine theta, 1.2 meters times sine of 32 degrees. I think that's going to be important later if we're going to find v squared over r, so we might as well just find r here. Hello. Clear. Okay. 1.2 times sine 32 degrees. It's still in degrees mode, which is good. And I got r is equal to 0.6359 meters. Okay. So I know that now. Next step, what I think I'm going to do here, let's draw a force diagram. Here's the tension going up and to the left, and there's, actually I think by the Z rule, I guess, there's your theta. Here is the gravity force down. I think those are the only two forces on the ball. And what we're going to do is define y to be up and r to be towards the center of the circular path, because, oops, that's r, because a sub r is to the left here. And we want to have all the acceleration in one direction, and we want to have that a sub y is equal to 0. So that means that the forces in the y direction must all sum to 0. So the forces in the y direction are going to be t in the y direction minus mg, and equals 0. And then, so we have to actually make this triangle here. Here's your theta. Here's a t in the y direction. Here's a t in the r direction. Here's your right angle, and here is t, the actual tension. So I think that sine theta is tr over t, and cos theta is ty over t. Okay, good. So ty is equal to t cos theta is going to be equal to mg. So t is going to be equal to mg over cos theta. So that might be important later. We now know what the tension is, and that's just to keep the ball from going up or down. Now what keeps it going in a circle is the net force in the r direction has to be mv squared over r. That's what keeps it going in a circular path. So the sum of all the forces in the r direction, gravity just points in the minus y, so there's just this tr. So you've just got tr is equal to mv squared over r. From that triangle, it's t times sine theta equals mv squared over r. Oh, but we know tension from the y thing. So I've got mg sine theta over cos theta is equal to mv squared over r. So they didn't give you the mass of the ball, and luckily mass cancels on both sides of this equation. And you get, you can solve it out here, I guess, that g tan theta is equal to v squared over r. So v is equal to square root of gr tan theta. And I think we know all these numbers now because we worked out r. Remember I told you r was going to be important? I think you need that down here. So v is equal to, don't want that 2 there, square root of 9.8 times 0.6359 times the tangent of 32 degrees. Okay, so gotta find that. Square root button, where is it? Here, second square root. 9.8 times 0.6359 times tan 32 end bracket, we get 1.973 meters per second. See if that's on the list here. Yeah, 1.97. That's approximately equal to 2.0 meters per second, and that is A. Okay, question 4. A banked turn has a radius of 400 meters and is designed for cars traveling at 90 kilometers an hour. This means cars traveling at 90 kilometers per hour can stay on the curve without assistance from friction. So Fs is 0. What is the banking angle of this curve? Okay, so I'm just going to draw it up here. Remember, let's do actually like a rear view of the car as it's driving like into the page. So I don't know if you can picture that. There's the wheels, there's like, I don't know, the bumper and like the license plate and maybe the, I don't know, the windshield. I'm not very good at drawing cars, but you get me, right? There's the car going away from you. Here's the tailpipe, and this is the angle that we're trying to find, the banking angle, and it is accelerating in the r direction, which is off to the left here. So we can drive, and this is, by the way, v squared over r, as we know. That's the centripetal acceleration. So we can draw a force diagram, which is that there's a normal force. There's no friction force, because they say there's no friction force, and then there's mg pulling it down. So what we do here is, actually it's very similar to the question 3, isn't it? Is going to define y to be up and define r to be towards the center of circular motion. Once again. So that what we can say is that it's not accelerating up or down. We can say that the sum of forces in the y direction equals 0, since a sub y is equal to 0. I'm accelerating up or down. So I can add those up. I've got, here, I have to do another triangle here. If this is the normal, and this is the normal in the r direction, here's your right angle, here's your y, so where's the theta? So if this is normal, this is theta, then this is going to be 90 minus theta from here to here, so this will be theta right here. So what that means is that sine of theta is equal to n r over n. Like I say, again, this is really reminiscent of the ball going in a horizontal circle, but and n y over n is cos theta. So what that means is that you've got n sub y minus mg equals 0. So n times cos theta is equal to mg. So that means that n is equal to mg divided by cos theta, which I think is going to be important later. You then also know that f sub r is mv squared over r. So all the forces in the r direction, which in this case is just m sub r, which is equal to n sine theta is mv squared over r. And again, we already solved for n using by balancing the y forces. So we've got mg sine theta over cos theta, mv squared over r. Again, by either good luck or just good planning, m's cancel. So we're trying to solve for theta, tan theta, v squared over g times r. So theta equals tan to the minus 1 of, whoopsie, I can't put 90 in there because that's not SI units. And I'm going to use G and R, which are both going to be in meters and meters per second squared and meters. So I need to first convert V, 90 kilometers per hour, times 1,000 meters per kilometer, and then divided by 3,600 seconds per hour. That way the hours will cancel hours, and I'll get this in meters per second. So let's do that. I should have done that earlier. So 90 kilometers an hour times 1,000 divided by 3,600. Oh, it's 25. So V is 25 meters per second. That's that special speed where you don't need assistance from friction. So, yeah, boy, I almost blew that. Divided by 9.8 times 400 meters. So I can do I have to do a shift, 10 to the minus 1, 25 squared divided by, open parentheses, 9.8 times 400, close parentheses, 9.05, and it's in degrees mode, so it's 9.058 degrees. And I guess, yes, it's closest to, to beat. Okay, question 5. A cart of mass m begins at rest. So this is like the initial, initial. And is connected to a spring of spring constant k, which is compressed a distance x away from its equilibrium. It is released rolling to the right with no friction. It encounters an upward curve in the track and reaches a maximum height h above its starting position. Which choice is the best equation for estimating h? Okay, this is a conservation of energy question. Okay, so initial energy is just going to be 1/2 k x squared. There's no kinetic because it's at rest, and it's at h equals 0, I guess. And then what happens here is that this, if it's maximum height, so max height, this is also at rest, because that's where it's going to turn around. So E final is just going to be m times g times h, because the spring is uncompressed and it gets to its maximum height. So you just say conservation of energy, E initial equals E final. There's no work done or anything like that, so it's just 1/2 k x squared equals m g h. You're trying to estimate h, so h is equal to k x squared over 2 m g, which looks like answer C. Okay, let's go on to question 6. Two forces impart impulses to a hockey puck which can move with no friction on an icy surface. Shown is the trajectory of the puck's motion in the xy plane, which is the result of these forces. The numbers correspond to successive clock readings that are marked on these force graphs. Okay, 1, 2, 3. Which pair of graphs shows the time dependence of the x and y components of the sum of forces exerted on the puck, which could result in this trajectory? I see. Yeah. So there's a hit here at 1 and a hit here at 2. So at 1, what happens is the trajectory, I think it must have initially been going like V0, going up, and then this is V1, still going up, but now it's going to the right. So what's happened here is that there's been delta px is positive. So that must have required plus Fx force, an impulse, over a small amount of time. And then what happens is that V2 is now going purely horizontally, so it's lost. It's still got this horizontal motion, but it's lost its vertical motion. So I would say that delta Py is, this is at 1 and this is at 2, is negative. So what it means here is that at t equals 2 seconds, there's an Fy, like a negative Fy impulse force. So what we're looking for is at 1 second, a plus force, and then at 2 seconds, a negative Y force. And nothing from the Y at 1 and nothing from X at 2, actually. Look at that. The answer is A. Just check the other ones. This has got 2 positives. That's not right, because this would speed it up even more in the Y direction. This has a X force at 2 seconds, which that's not right. Nothing at 1, so that's wrong. This is wrong. All these have something happening at 2, which is wrong in 1. So I think the only one that makes any sense is A. Okay, good. On to question 7. Let me just quickly check the time here. It's 6:33, so we're doing great for time, because we're 7 questions in out of 11 questions. CN Tower record holder Sean Stevens Whale climbed the CN Tower's 1,776 steps in 9 minutes and 55 seconds. This is a vertical climb of 350 meters up. So H is 350 meters. And Sean has a mass of 79 kilograms. If Sean's body is 20% efficient at converting chemical energy into mechanical energy, how many food calories of chemical energy does he expend during the CN Tower climb? Note, 1 food calorie equals 4,186 joules. And there's the number of food calories. Okay. Boy, I hope it's more than 0.58 calories for him to climb this entire tower. I don't know what it's going to be, but let's just work it out. So, mechanical energy is just mgh, right? Will be, I think, mostly, I mean, he might move a bit, but from gravitational potential energy. He has to gain all that gravitational potential energy to get up to the top of this tower. That's what's going to really tire him out, and energy. So E, delta E or something, is equal to mgh. And then efficiency of converting chemical energy, 0.2, to mechanical energy, means that the chemical energy is actually going to be the mechanical energy, delta E mech, divided by the 0.2. It's going to take more chemical energy to get that much mechanical energy, because it's only 20% efficient to, I guess, convert the chemicals in your stomach into, actual action from your legs. So it's going to be mgh divided by 0.2. So 79 kilograms times 9.8 times 350 divided by 0.2. 79 times 9.8 times 350 meters divided by 0.2. Oh yeah. So delta E chem is 1354850, and that's going to be in joules. But we were given 1 food calorie is so I'm going to multiply this by 1 calorie per 4,186 joules to cancel out the joules. Divide this by 4186, gives you 323.6 calories. Okay, so it's around, well, it's close. It's actually around 320 calories. Good. Question 8. My shaving mirror is attached by 2 supports to the wall of my shower. So gravity pulls the mirror down. And there are 2 forces from the wall acting on the supports of the mirror. F1 acts at point 1 and F2 acts at point 2. So these are the forces acting on the mirror from the wall. Which is the following statements correct about the horizontal components of F1 and F2? Okay, so the trick here is what I have to do is first find F2 by setting the axis at 1. So if I draw this, here's 1. This is the axis of rotation. Okay, and here's mg, and here is 2. So what's going to happen is that mg exerts a clockwise torque around 1. So that means is that F2 exerts counterclockwise torque. So it's going to have to rotate it counterclockwise, so it's going to have a horizontal component is to the right. This is F2. F2 to the right. So that's that. And then next, find F1 by setting the axis at 2. So same thing. Here's your axis. Here's your mg, which pulls at the center of mass here. And here's your 1. So mg again exerts a clockwise force, clockwise torque. We need the torques to be 0. Some of the torques. So therefore F1 exerts counterclockwise torque. So it has to twist it the other way, so this is going to have to be towards the left. F1 to the left. Which I think is why there's a suction cup on the mirror pulling it in that way, and this can just be a stick. You can kind of imagine that, right? It has to pull here, and it has to push here. This is F1. And that's the only way you can have the sum of all the torques on the thing is equal to 0 about any axis, about the rotation axis at 1 or the rotation axis at 2. So F1 has a horizontal component to the left. Nope. F1 has a horizontal component to the left, correct? And F2 has a horizontal component to the right, so the answer is E. Okay, question 9. A uniform ladder leans against a frictionless wall as shown. Static friction between the floor and the ladder is sufficient so that it does not slip. Okay, it's static equilibrium. The angle between the floor and the ladder is 72 degrees. And the angle between the wall and the ladder is 18 degrees. I guess those make 90, which is right. So this is a 90-degree angle. The ladder has a mass of 7 kilograms, kg, and L is equal to 2.5 meters long. What is the magnitude of the normal force of the wall on the ladder? So you've got to find N. Okay. So the system here is the ladder. And I think since I care about this normal force up here, there's also going to be a gravity acting down. There's going to be the friction force acting on it there. There's going to be another normal force, 2, acting there. I'm going to choose the rotation axis to be the foot of the ladder, where I don't care about a bunch of these forces, and then I'll just work out the torques of all the other forces. Choose rotation axis equals bottom of ladder. where there's a bunch of forces here that I don't care about. So I'll call this axis. Okay. So, and let's draw an extended force diagram. So there's ladder. The forces I really care about here are going to be N, and there's going to be mg, and here's my rotation axis, and I guess again there's Fs, and there's going to be normal, I don't know, call it normal 2, the normal force I don't care about. And what I can do, I'm going to say that the sum of all the torques is equal to 0, since it's not rotating. And I'm going to have to find, I think this is going to be the lever arm called dg of the gravity force. And then this distance from here to here is going to be dn, the lever arm of the normal force there. So I think what I can do is I could draw some triangles and start with this one, I guess. If this, so by the Z rule, I think this is the 18 degrees. So let's say theta is 18 degrees. Then this is dg, and this is L over 2, half the ladder length. So I think that I'm going to use sine theta as dg, lever arm of the gravity, divided by L over 2. So dg is equal to L over 2 sine of 18 degrees. And then to find the normal force, the lever arm of the normal force, same triangle here, but now I've got L, the whole length of the ladder, and this is dn over here, and there's your theta. So now it's cosine theta is the adjacent divided by the length, the whole length of the ladder. So I've got the lever arm of the normal force is equal to L cosine theta. So the sum of all the torques here, I'm going to say is equal to, there's 0 plus 0. Those are the torques at the bottom because they're acting at the rotation axis, no torque. And then this is a counterclockwise torque from gravity. So it's plus mg times d sub g. So 0, by the way. And then the normal force is clockwise, so that's a negative torque of the normal force that I'm trying to find times d sub n. But I've already found these using the geometry, so I'll just plug d sub g into here, and I'll plug d sub n into here, these lever arms. And I've got, these are going to equal to each other since the whole thing sums to 0, so I've got m times g times L over 2 times sine of theta equals normal force times L times cosine of theta. And I think either by luck or good planning I can divide both sides by L and get rid of that, and I've got mg over 2 sine theta is equal to n times cos theta. So n here is just equal to mg sine theta divided by 2 times cos theta. So mg over 2 times tan theta, I guess. So it's 7 times 9.8 times tan of 18 degrees divided by 2. Let's work that out on my calculator. 7 times 9.8 times tan 18 degrees. And don't forget to divide by 2. 11.14 newtons. So yeah, that's closest to answer A. Okay, last multiple choice question. A rigid uniform horizontal bar of mass m1 equals 1.5 kilograms is supported by 2 vertical strings. String A is attached to the top of the bar. 0.25 meters from the left end is connected to the fixed ceiling above. String B is attached to the bottom of the left end of the bar and is connected to the floor below. Okay, I get it. and a plant of mass MP is 3.2 kilograms is hanging from the right end of the bar. What is the tension in string A? Okay, so let's just say that the system here is equal to the bar. And I can find the tension in the plant here. It's just going to be M plant times G, right? So the tricky ones here are the tension in string B and the tension in string A. And I don't care about the tension in string B, so I think what I'm going to do is choose the rotation axis to be point B there. Rotation axis to be the left end of the bar, because that's where the tension is that I don't care about. But basically, yeah, I'm just doing that the sum of all the torques around that point is equal to 0. So there's going to be a counterclockwise torque from string A, yes, and a clockwise torque from string B, so, or from the plant. So yeah, I've got this TB I don't care about. I've got this TA acting at some distance dA, I guess. And I've got this, which is M plant times G. That's the tension in this string, actually, in order to support that plant, is going to be at some distance, the whole, length there. dG, I'll call it again. But we know that length. So the sum of all the torques... oh, wait a second. I forgot one thing here. What about the mass of the bar? M1 times G. I'll call that D1. There's another torque there. I almost forgot about that. Just the weight of the bar, of the uniform bar, right? So the sum of all the torques is equal to 0. Is going to be 0 from that left end, and then it's going to be a positive plus TA times dA. And then it's going to be, these are both going to be clockwise torques, so they'll be negative. So minus M1 times G times D1, and then minus mass of the plant times G times dG. Okay, so, and I can rearrange that. The tension A times dA is equal to M1 G D1 plus MPG times dG. So the tension A is equal to M1 D1 plus mass of the plant times that length of the whole bar, all times G, all divided by dA. So I've got a 1.5 kilograms from M1 times 0.5 meters plus 3.2 kilograms from the plant times 1 meter, all times 9.8 divided by 0.25. So TA is equal to, I've got 1.5 times 0.5 plus, well, just 3.2 times 1 times 9.8 divided by 0.25. I got 154.84 newtons. So that's going to be closest to 150 newtons. Great. All right, so we're done the multiple choice. Let's just check the time. It looks like it's almost 6:50 there. Got till 7:30, but I guess I am the professor, so hopefully this doesn't take me the full 80 minutes. But let's look at the written problem. So it says, a 920 kilogram sports car collides into the rear end of a truck stopped at a red light. So I thought there was going to be a collisions question eventually. The vehicle is locked together, so this is an inelastic collision. The brakes are locked, meaning that the two vehicles skid forward, so it's sliding friction 2.8 meters before stopping. Okay, so this is a 1D problem. The police officer estimating the coefficient of friction between tires and road to be 0.8. Calculates the speed of the sports car at impact. What was that speed? Okay, great. Okay, let's start with the sketch and translate. And basically, there are two things that are happening here. One is the collision, which is going to conserve momentum, and then the next is the skidding, which is going to conserve energy. And so I'm going to break this up into 3 separate times, so that at the beginning you have the mass of the car, which is 920 kilograms, and it's going at some speed you don't know, v1 of the car. That's what you're trying to find, so need this. And then the mass of the truck, which is 2,300 kilograms. Sorry, put the handwriting there. This V1 truck is equal to 0. And then they collide. And so what happens is that now they're stuck together. I can sort of say mass total is equal to 920 plus 2,300. I think I might as well just work that out actually. 920 plus 2,300 is 3220 kg. That's going at some V2. And then 3, what happens is that whole thing will slide some distance d, so that V3 equals 0, and this is m total. Okay, and what will happen is that there will be some kinetic friction, which will conserve energy here. So from 1 to 2, what we're going to do is conserve momentum, P initial plus J is equal to P final. And from 2 to 3, what we're going to do is conserve energy. So that energy initial plus the work is energy final plus delta U internal. Okay. So in our simplify and diagram stage, that's when we can do these energy or momentum bar charts, I guess. So we can just say that from 1 to 2, it looks something like this. You've got the initial, P initial of the car, and then the P initial of the truck, which is 0, and then the impulse, which is 0, is equal to the P final of the total. And then from 2 to 3, what happens is that you've got your, that thing is sliding, so the kinetic energy initial plus the work is equal to the kinetic energy final plus the delta U internal, which is equal to the Fk times d. That's where all the energy goes. So when we get to our represent mathematically stage, what you've got is this equation, which is that the mass of the car times the V1 of the car plus 0 plus 0 is equal to the mass total times V2. And then from this diagram, you've got 1/2 m total times V2 squared, that's initial kinetic, is equal to Fk times d. And the thing about the Fk is that Fk is equal to the normal force times mu sub k. And if you have the normal force acting up and m total g acting down, and this is the y direction, and a sub y equals 0, so the sum of all the forces in the y direction equals 0, then what that means is that normal force equals m total times g. So what you end up with is that m 1/2 m total times v2 squared is equal to mu sub k times m total times g times d. And you can cross out the m total on both sides of that energy equation to solve out for V2. V2 is going to end up being the square root of 2 times mu sub k times g times d. And we're going to sub that back in to here. And we're going to say that, and I can actually do to solve and evaluate stage now, which is to say that V1 of the car is equal to m total divided by the mass of the car times this V2, square root of 2 times mu sub k times g times d. And I think we have all these numbers. It's going to be 3220 kilograms for both the objects, 920 for the car, times the square root of 2 times 0.8 times 9.8 times 2.8. Square root all that. So let's clear this. 3220 divided by 920 times the square root of 2 times 0.8 times 9.8 times 2.8. And I get V1 of the car is equal to 23.19. So, and that's meters per second. V1 of the car. So the initial speed of the sports car was 23 meters per second. And I think if you times by 3.6, you get that's around 80 kilometers per hour. Not an unreasonable speed. Whoop. Bit fast to be crashing, but that's why they slide so far. And that is it.